The question that I have is, could you explain the process of consolidation of soil? So here's a little spring water model that is commonly used to explain the process of consolidation. Basically, we have a cylinder with a piston, and the piston is sitting on a spring, elastic spring, that has a constant, spring constant K. So the force displacement relation for the spring looks like this. And this cavity here is filled with water. Let's just say the initial length of the spring is little l. There's no load on there right now. There's a little opening here, but the opening is closed at this point. I'm going to take this system and apply a load P on the piston rod. The valve is still closed. Let's just say the load is 10 units. This 10 units has to be supported by something for equilibrium, right? But the valve is closed at this point and therefore water cannot come out. But we know the water is an incompressible material and therefore there's not going to be any deformation on water. So if there is no deformation on water, there is no deformation on the spring. And therefore force on the spring has to be zero, and therefore the entire load of 10 units will have to be carried by water, and obviously in the form of pressure acting at the bottom of the piston. Now let's just say we open the valve, but let's assume that the valve is so small that the water can only come out very, very, very slowly. As the water slowly oozes out, the piston gradually sinks. As it sinks, the compression of the spring increases, and therefore the force on the spring gradually increases. So in this example, it went from 0 to 2 to 4 to 8 and finally to 10 units. So at this point, the water doesn't have to carry any load. So there's no force carried by water. But between this initial stage and the final stage, both the spring and the water carries a little bit of load. The spring force keeps increasing, the water force keeps decreasing, and eventually the spring carries the entire load of 10 units. But it's going to take some time. And how long does it take? Depends on the size of the opening of this little valve right there. Now let's compare this system with the consolidation setup that we talked about in the earlier video. The water compares with water, but the collection of solid particles serve as the spring. Then what about the opening? Well, the pore space between the solid particles serve as the opening. Water comes through the pore space between the particle, but it's going to take some time. So it depends on the porosity of the soil. In other words, it depends on the permeability of the soil. So as the water seeps out of the soil, the piston keeps coming down. So initially, the water in the soil actually carries the entire applied load of 10 units. And then gradually, as the water comes out, the solid particles begin to carry some of the load. So as the solid particles begin to carry some of the load, the force carried by the water decreases. So eventually, after a sufficiently long time, the solid particles carry all of the load, water carries zero load. And here the load carried by water compares with the pore water pressure. And the load carried by solid particle compares with the effective stress, effective intergranular stress. So here's a translation between the hypothetical spring water model and the real soil system. Think of this as the total stress. This total stress is going to be carried by both the effective stress and the pore water pressure. So initially when time equals 0, the effective stress is 0, pore pressure is 10. And then as the time increases, effective stress increases and the pore pressure decreases. Eventually, the effective stress becomes exactly equal to the applied pressure 10, and the pore water pressure becomes equal to 0. This is the consolidation process. So now we can kind of go back and look at something we did earlier. Remember this curve, right? Settlement versus time curve for 4 different load steps. We went from 0 to 2 psi, 2 to 4 psi, 4 to 8 psi, 8 to 16 psi. So during this process, I said consolidation takes place, right? So exactly what is happening? Well, the applied pressure of 2 psi is first taken completely by water, but then during the process of consolidation, water pressure dissipates, and eventually the applied pressure of 2 psi becomes exactly equal to the effective pressure in the soil. And that process repeats, it continues. So this 4 psi becomes the effective stress at this point, and the 8 psi becomes the effective stress at this point, and the 16 psi becomes the effective stress at this point. But in between, of course, the effective stress is less than 16 psi because part of that is taken by water. So what I have actually plotted here is a relationship between the weight ratio and the effective stress. So I should really call this sigma v prime. So just to emphasize, if you plotted the weight ratio against the total vertical stress, you're not going to get a nice unique curve like this. So you have to plot the weight ratio as a function of the vertical effective stress. Just to be clear, even the overconsolidation ratio is defined in terms of effective stresses. Effective pre-consolidation pressure divided by the initial effective vertical stress.